constant. Rate constant of the second step and equilibrium constant for first step, they are constant. So the product is a constant. And I call K. That's the rate constant for the overall reaction, we say, right? K. So it's going to be K, which K is equal to K2 times K equilibrium. Times A2B2. Right? So we found the same rate law, actually. There are two different mechanisms, but the rate law comes up to be the same on these two mechanisms, right? Now somebody will wonder, what does this K equilibrium is? We talked about in lecture about rate constant, now you're talking about K equilibrium. Really, realize now, coming from Chem to B, right, that the equilibrium constant of a reaction is nothing else but the rate of rate constant. You realize that? Huh? And just because the rate constant depends on temperature, equilibrium constant depends on temperature. Good. Reactants to products, and products to reactants. This is the K and K minus. That minus is just a symbol, right? Reverse. Forward reaction, R to B. Reactants is R, product is P. Reverse reaction, reactants is P, and product is R. Yes? Forward, reverse. Rate constants for each of these two reactions. For the forward reaction, rate constant K. For the reverse reaction, K minus or dash, we want to say, dash the reverse. The rate constant for the reverse reaction. Right? Now, when this system is in equilibrium state, what does it mean? By definition, the rates of the forward and reverse reactions are equal. Yes? So, equilibrium state means that the rate of forward is equal to the rate reverse. The rate of the forward reaction will be what? We make it a simple case here. So the forward will be rate constant times the concentration of the reactant, right? Just use a simple equation to make things easy. The reverse reaction is going to be rate constant, which is what? This times concentration of the reactant. In this case, for the reverse, the reactant is what? P, right? I should have probably put A and B better. This cannot have B. It's confusing, right? I can change it. A and B. Just because there's a reverse of the system and, you know, it will be confusing, reaction and product, right? So, for this one, it will be K times A, concentration of A, and then the reverse is going to be K times the reactant, which is now B. Okay? Now, this one, I can write it like this. Right? I can write this one like that, can I? And really that ratio B divided by A is what? Isn't the K equilibrium? That ratio, this one here, is really K equilibrium, isn't it? So you can see the equilibrium constant in a reversible system reaction is actually the ratio of K forward divided by K reverse. Can you see that? Same thing. So that's why we do it this way. Okay, you want to see the third case? And we finish. If you deduce the rate law for the third mechanism, again, you can go and see we have 3 steps now, right? We have 3 steps. The slow is this, yes? So for the third step, which is slow, if you write the rate law, it should be equal to what? Rate should be equal to, third step, we have K3 times BA2 molecule times B. So now we have 2 equilibrium systems, right? 2 reversible systems. So we can write 2 equilibrium constants, K equilibrium 1 for the first one, which is going to be like this. And K equilibrium 2 which will be BA2, BA2. So now, because of these two equations, this rate law for the slower step, which will be the rate of our overall reaction, will be rate K3 times K equilibrium 2 B A2 again B, and we can manipulate it a little bit algebraically. It will become B squared, this and that will become B squared. And now we can use this. It will become K3, K equilibrium 2, K2, K equilibrium 1.
Professor?
Yes?
Please slow down a little.
B2. And from this one, you can see that you really have an equilibrium, we have a constant here, which is equal to K3 times K equilibrium 2 times K equilibrium 1. All this is a constant. All these you can call it K. K. So what remains is A to B2. Huh, very interesting, huh? So for each of these three different mechanisms, they're all completely different mechanisms. Actually, each one of them has the same rate law. And it is different rate law than the experimental rate law. Remember that, right? Okay, so now let's answer the questions. What's the question? D. Question D says, which of these three mechanisms is the least probable one and why? So you have to look at that. Here's the three mechanisms. Watch which one of these three mechanisms is the most, the least probable and why? Which one?
Yeah.
Right? Why is 2? Wait a minute, first, second, and third, right? Yeah, right. Okay, so the second one is the most improbable, the least probable. Why? As he said. Because it involves a step that is thermonuclear, that's molecularity 3. 2B molecules and 1 A2, right? A2 and that's 3 molecules at the same time to collide. Yes? And that's very improbable. So if you have a choice between the three, you would disregard that one because it's very unlikely to have 3 molecules at the same time collide, okay? There's a step like that. Okay, what's the other question? The other question is, if during the reaction 2 intermediates are detected, which of these three mechanisms is the most probable and why? Huh? Which one? Look at the mechanism again. You have to look at the mechanism to be able to decide. Okay? The third one, why? Well, it involves 2 intermediates. Right? If you can detect 2 intermediates, and this one shows you 2 intermediates, this one and that one, that's probably a correct mechanism. Probably, not for sure. Right? The other ones don't have 2 intermediates, you can see, they don't suggest intermediates. So if you see 2 intermediates, different ones in your experiment, then you say, forget about this, forget about that. Right? So what's the other question now? Yes?
For the least probable, how do we know that the second mechanism involves 3 molecules colliding?
When you see 2B plus A2, 2B is B plus B, and A2 is another molecule. So you have 1, 2, 3 molecules at the same time to collide. Because each step here is a single elementary step. That means molecularity 3. Molecularity 3 means 3 molecules at the same time colliding. That's pretty improbable. You can play pool to see if that can happen. Huh? The third one is the most probable of the 3 because it tells us if you can detect 2 intermediates during the reaction, which is most probable. So which one of these 3 mechanisms has 2 intermediates? This one, right? And the last one is what? The last one is answer to what?
Yeah.
Can the observed rate law expression distinguish among these mechanisms? No. Each of these mechanisms has the same rate law, like the